Suppose I ask for H4 hypothesis, that is, if I consider P is equal to P naught against P is not equal to P naught. In place of P less than or equal to P naught, if I modify that, then we can, this region will not come, only this portion will come, and we will analyze the behavior of this function in a more appropriate fashion, because there will be two regions. One will be corresponding to x by n greater than P naught. We have already seen that in this region we are getting the function to be a decreasing function. However, if I consider x by n less than or equal to P naught, this value will become positive, and therefore, lambda star x will become an increasing function. So, let me just give the complete analysis for the two sided testing problem. If we consider the two sided alternative, that is H4 P is equal to P naught against K4 P is not equal to P naught. In that case, lambda x, that is equal to simply P naught to the power x 1 minus P naught to the power n minus x divided by x by n to the power x 1 minus x by n to the power n minus x. So, lambda the behavior of lambda star, we have seen that derivative of d by dx of lambda star x, that is equal to log of n minus x into P naught divided by x into 1 minus P naught. So, this is less than 0 for x by n greater than P naught, and it is greater than 0 for x by n less than P naught. So, the nature of the function is then that it is increasing, and then for x by n less than P naught, it is increasing. So, if I am treating it as a function of x, then it is firstly for x by n, it is increasing, and then it is decreasing. On this side I have x, on this side I have lambda x or lambda star x. So, now the region lambda x less than or equal to c, that is equal to these two regions. So, lambda x less than c is equivalent to x less than c 1 or x is greater than c 2, and we should have probability of c 1 less than or equal to x less than or equal to c 2 is equal to 1 minus alpha, where x follows binomial n P naught. So, this c 1 and c 2 can be determined from the tables of binomial distribution. I have shown you that even in the case of discrete case, the likelihood ratio test can give a nice and elegant solution. However, if the distribution is not in an exponential family, let us consider one example. Let x 1, x 2, x n be a random sample from an exponential population with location parameter. That is e to the power theta minus x is the density function. So, the likelihood ratio function is e to the power n theta minus sigma x I, which I can write as e to the power n theta minus x bar. This is for x 1 greater than theta, it is equal to 0 if x 1 is less than or equal to theta. So, naturally you can see that L is increasing in theta. So, theta hat is equal to x 1, this is over omega. So, L hat omega is nothing but e to the power n x 1 minus x bar. Let us consider omega h. For omega h, if I am considering, now this is an increasing function. In fact, you can see at theta is equal to x 1, this will be this value, but it is going like that. So, for omega h, theta hat omega h, that will be equal to x 1 if x 1 is less than or equal to theta naught, and it is equal to theta naught if x 1 is greater than theta naught. So, L hat omega h, that is equal to e to the power n x 1 minus x bar if x 1 is less than or equal to theta naught, it is equal to e to the power n theta naught minus x bar if x 1 is greater than theta naught. So, the ratio, that is L hat omega h by L hat omega, that is equal to 1 if x 1 is less than or equal to theta naught, and it is equal to e to the power n theta naught minus x 1 if x 1 is greater than theta naught. So, here in this case we will accept h 1, and in this particular case, if I am considering e to the power n theta naught minus x 1 less than c, then this is equivalent to x 1 greater than c. So, this c will be determined from the size condition, probability of x 1 greater than c, when theta we are taking maximum for theta less than or equal to theta naught. This should be equal to alpha. Now, what is the distribution of x 1? That is equal to n e to the power n theta minus x for x greater than theta. So, if I consider probability of x 1 greater than c, that is equal to e to the power n theta minus c. So, this value is actually e to the power n theta minus c. So, if I take supremum theta less than or equal to theta naught, that is equal to e to the power n theta naught minus c, that is equal to alpha. That means, c is equal to theta naught minus log of alpha by n. So, the likelihood ratio test is, so when x 1 is greater than theta naught, reject h 1 if x 1 is greater than theta naught minus log of alpha by n. Now, we take up the likelihood ratio test for 2 sample problems. So, likelihood ratio test for 2 sample problems. To start with, I consider random samples from 2 normal populations. Let us consider independent random samples x 1, x 2, x m from normal mu 1 sigma 1 square, y 1, y 2, y n from normal mu 2 sigma 2 square. Let us consider the hypothesis, say, for testing of mu 1 less than or equal to mu 2 against say mu 1 greater than mu 2. We assume here that sigma 1 square is equal to sigma 2 square. In this case, we have derived the UMP unbiased tests. When this is not equal, that is sigma 1 square is not equal to sigma 2 square, it was known as a Behrens-Fisher situation. So, our parameter space is mu 1 mu 2 sigma square, mu 1 is real, mu 2 is real and sigma square is positive, and omega h, that is mu 1 mu 2 sigma square, mu 1 is less than or equal to mu 2 and sigma square is greater than 0. Let us write down the likelihood function. The likelihood function is given by L mu 1 mu 2 sigma square x and y. So, that is equal to 1 by 2 pi sigma square to the power m plus n by 2 e to the power minus 1 by 2 sigma square sigma x I minus mu 1 square plus sigma y j minus mu 2 square. Log of L is equal to minus m plus n by 2 log of 2 pi minus m plus n by 2 log of sigma square minus 1 by 2 sigma square sigma x I minus mu 1 square plus sigma y j minus mu 2 square. So, if I consider the maximization over the full parameter space, so let me write this as small l. So, del L by del mu 1, that will give me sigma x I minus mu 1 by sigma square, that is n x bar minus mu 1 by sigma square. So, once again less than 0 if mu 1 is greater than x bar, it is greater than 0 if mu 1 is less than x bar. So, maximum is attained at x bar, that is mu 1 head omega is equal to x bar. Similarly, if I take del L by del mu 2, that is equal to n y bar minus mu 2 by sigma square, that is less than 0 if y bar is less than mu 2, it is greater than 0 if y bar is less than mu 2. So, maximum is attained at y bar, that is mu 2 omega head, that is equal to y bar. Let us also consider the maximization with respect to sigma square. So, we get minus m plus n by 2 sigma square plus 1 by 2 sigma to the power 4 sigma x I minus mu 1 square plus sigma y j minus mu 2 square. So, that is equal to, if I take m plus n by 2 sigma to the power 4 out, then I get 1 by m plus n sigma x I minus mu 1 square plus sigma y j minus mu 2 square minus sigma square. Once again it is less than 0 if sigma square is greater than 1 by m plus n sigma x I minus mu 1 square plus sigma y j minus mu 2 square. It is greater than 0 if sigma square is less than 1 by m plus n sigma x I minus mu 1 square plus sigma y j minus mu 2 square. So, sigma omega head square, that is attained at this value where mu 1 and mu 2 are replaced by their respective maximum likelihood estimators. That means, it is attained at sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n. So, if we consider L head omega, so L head omega is equal to 1 by 2 pi sigma omega head square to the power m plus n by 2 e to the power minus m plus n by 2. Now, let us consider over omega h. Omega h. Over omega h, what is happening, that let us look at the derivatives here. The maximization were occurring at x bar and y bar for mu 1 and mu 2. Now, we are saying mu 1 is less than or equal to mu 2 over omega h. So, when x bar is less than or equal to y bar, we can treat them as such. So, when x bar is less than or equal to y bar, we take mu 1 omega h head is equal to x bar, mu 2 omega h head is equal to say y bar, and sigma omega h head square, that is equal to 1 by m plus n sigma x I minus x bar square plus sigma y j minus y bar square. There is no change. In this case, the ratio, that is L head omega h by L head omega, that is equal to 1. So, we always accept h 1. The hypothesis that I mentioned here, mu 1 less than or equal to mu 2 against mu 1 greater than mu 2. So, we always accept h. So, that is alpha is equal to 0. Now, the other possibility is when x bar is greater than y bar. Now, when x bar is greater than y bar, then we analyze. Firstly, you look at the behavior with respect to mu 1. Now, with respect to mu 1, you see it is initially increasing up to x bar and then decreasing. So, now if y bar is less than x bar, then we will have to modify this thing. What we do? Fix mu 2 first, say, okay, and then the maximum with respect to mu 1 is mu 1 head is equal to minimum of mu 2 and x bar. Now, if x bar is less than mu 2, then mu 2 head will be equal to maximum of x bar y bar, that is by finding the maximum with respect to mu 2, and we always accept h. However, another case occurs when if x bar is greater than mu 2. In this case, the d L by del mu 1, that is equal to m x bar minus mu 1 by sigma square. I think I wrote a little bit wrongly in the first place. This was m times, not n times. So, this one will become greater than 0 on omega h, because we are having mu 1 less than or equal to mu 2. Okay. So, with respect to mu 1, the maximum is attained at the line mu 1 is equal to mu 2. So, in this case the log likelihood, that is L, I can write as minus m plus n by 2 log of 2 pi minus m plus n by 2 log of sigma square minus 1 by 2 sigma square sigma x I minus x bar square plus sigma y j minus y bar square minus m by 2 sigma square x bar minus mu 1 square mu square plus n by 2 sigma square y bar minus mu square. So, if I consider del L by del mu, then I will get mu head is equal to m x bar plus n y bar divided by m plus n. That is the grand mean, that is mu 1 omega h, mu 2 omega h, because I have assumed them to be equal here. And sigma omega h head square will also get, because there we were getting x I minus mu 1 and y j minus mu 2. So, this will become simply sigma x I minus x bar square plus sigma y j minus y bar square plus m n by m plus n x bar minus y bar square. So, L head omega h, that becomes equal to 1 by 2 pi sigma omega h square to the power m plus n by 2 e to the power minus m plus n by 2. Now, the rejection region is we reject H when lambda x, that is L head omega h by L head omega, that will become sigma omega head square by sigma omega h head square less than, say, some to the power n by 2 will come. So, I am to the power m plus n by 2 less than some c, or we can say sigma omega head square by sigma omega h head square is less than c 1. Now, we substitute the values here. This is sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n, and in the denominator then I have sigma x I minus x bar square plus sigma y j minus y bar square plus m n by m plus n x bar minus y bar square. This is less than c 1. You take the reciprocal and then subtract, then this will give us actually m n by m plus n x bar minus y bar square divided by sigma x I minus x bar square plus sigma y j minus y bar square greater than, say, some c 2. Note here that x bar is greater than y bar, x bar is greater than y bar. So, this means I can take the square root here m n by m plus n x bar minus y bar divided by s p greater than some c 3, where s p square is nothing but sigma x I minus x bar square plus sigma y j minus y bar square divided by m plus n minus 2. So, the condition that we will be getting here is probability of root mn by m plus n x bar minus y bar by s p is greater than C 3 when mu 1. So, this is for general mu 1 mu 2, we have to take the supremum when mu 1 is less than or equal to mu 2. This should be equal to alpha. Now, note here root m n by m plus n x bar minus y bar minus mu 1 minus mu 2 divided by S p. This will follow t distribution on m plus n minus 2 degrees of freedom. This part we have considered earlier in the sampling distributions in my lectures on probability, because you are having actually x bar following normal mu 1 sigma square by m, y bar follows normal mu 2 sigma square by n, then sigma x I minus x bar whole square by sigma square, that follows chi square distribution on m minus 1 degrees of freedom, sigma y j minus y bar square by sigma square follows chi square distribution on n minus 1 degrees of freedom, and these are all independent. So, x bar minus y bar minus mu 1 minus mu 2, then if I consider this will follow if I divide by sigma root 1 by m plus 1 by n, this will follow normal 0 1, and sigma x I minus x bar square plus sigma y j minus y bar square by sigma square, this follows chi square distribution on m plus n minus 2 degrees of freedom, and we take the ratio that will give me this as t distribution. If this is the t distribution, then this probability if I consider, probability of root m n by m plus n x bar minus y bar by S p greater than C 3, that is equal to probability of root m n by m plus n x bar minus y bar minus mu 1 minus mu 2 divided by S p greater than C 3 minus root m n by m plus n mu 1 minus mu 2 by S p. Now, this is a t distribution on m plus n minus 2 degrees of freedom. So, we are saying probability of a t variable on this is bigger than C 3 minus root m n by m plus n mu 1 minus mu 2 by S p. Now, mu 1 minus mu 2 is less than or equal to 0. Actually, if I increase mu 1 minus mu 2, then this term will decrease. If this term decreases, this probability will increase. So, this probability is increasing in mu 1 minus mu 2. So, on omega h, the maximum value will be attained at mu 1 minus mu 2 equal to 0. That is, the size condition becomes probability of root m n by m plus n x bar minus y bar by S p greater than C 3 when mu 1 is equal to mu 2. So, this means C 3 is nothing but T m plus n minus 2 alpha. You can compare it with the UMP unbiased test that we derived. This form is the same. So, in the likelihood ratio test, what is happening is that some part we are having slightly different in the one sided testing problems, but in the two sided testing problems this is exactly same as the UMP unbiased test. In the next lecture, I will derive this test, likelihood ratio test for mu 1 equal to mu 2 against mu 1 not equal to mu 2. We will also consider the testing for the equality of variances. So, sigma 1 square less than or equal to sigma 2 square, sigma 1 square is not equal to sigma 2 square. These hypothesis testing problems also I will consider in the next lecture.